the aim of what I'm trying to talk today is to take this as an example of an electronic system. You're doing a course on electronic system design. So this is an electronic system. And we'll walk you through some of our design considerations in making this particular system. Okay. So whenever you look at any system, there are specifications. And you have the technical specifications, that is one. The other important specification is also what is the price point that you want to sell this at. So if you want something, for example, going back to an oscilloscope, if I say that I want to have an oscilloscope that does 1 that does 100 megasamples per second, yes, it can be done. You can purchase the appropriate A to D converter and incorporate it into whatever system you're building. But that will have a trade-off in terms of the price. Okay. So when we started, really the aim was that let's keep this as low cost as possible so that we can easily ship it to as many students. We didn't know how long the pandemic will hit. We tried it with a small class of 10, but maybe we would have to have done it with a larger class of 200. Maybe we would have liked that other universities use it. So price was a very, very important design factor and also a constraint. So you will see that some of our design choices are actually driven by how to keep the component count low so as to keep the price low. Okay. So if you are making something and you have a different design constraint, then you will land up with a different design outcome. Fine. So take what we are saying in that larger context. One of the things, for example, that I'm sure I think the analog guys also have done is that you will see that both the kits that you have, the one that you have used and this one, gives you only single supply, that is 0 to 5 volts. Maybe it will give you 2.5. We give you, if you look on the, so we call our, so the way we have built this is that you have the breadboard. On the breadboard, you have a small board. That's our power supply board. Okay. And then you have another board that you can see that's actually designed as a daughter board which sits like a hat on top of a regular Arduino. Okay, that's the way we have designed this. Why? We'll talk you through. This was not our original design. We'll tell you why we came to this. But you can just look at that and then you will see immediately that there are two USB ports, and you will see that both of them are the big old fashioned USB ports, right? Again, it's a design choice. We'll tell you why. But I'll tell you now because many of you are fidgeting to connect it to the laptop. I'll tell you immediately as to why we have two ports and what we intend to be the correct usage of these two ports and what we will allow today because we are not going to do anything substantially dangerous. So all of you are going to connect this to your laptop. And so the laptop USB has sufficient power to drive this guy. Okay. So the port which is there on the main board, right, can be used to power everything, no problem. However, what you will find is that, sorry, let me step back. It can be done that way, but you have now the daughter board and you have the power supply board. Both of them have USB connectors. The intended use is that the main board gets connected to your laptop USB port. Okay, so data and power goes through that. That power is used only for our system. It's not used to power your circuit. We have tested our system. We know that there are no short circuits and all of that. So we are reasonably comfortable that it's not going to fry your laptop. We have fuses in there even then. Okay. The other power board which is there, we intend that it is powered using a standard phone adapter. We have given you the cable. So you can use, it's a USB B to the larger B form. So you can use that. You can use that to use a phone adapter and power the small board. Advantage of doing that is that even if you short something on the breadboard, nothing is going to really happen. The fuse will blow. There's a fuse on that small daughter board. That fuse will blow. You can change the fuse. Okay. So that was a safety element that we brought. No, that's not the fuse. We'll show you everything here. Okay. The one that you're touching is not the fuse. Okay. So I think with that, let me start because otherwise we'll just keep telling you stories. Great. So this is a big effort. So the main designer actually happens to be my father. I see also that many of you have brought your parents, and many of your parents are also very active parts of this, of the electron system design course. So it's something like that. So he's a retired electronics engineer. He also graduated from IIT Madras many years ago, worked in DRDO, and then now he's a freelance hobbyist. So so we have been doing this together. A lot of the design comes from him. I've looked at how to actually use it in a course, and what are the changes necessary from the point of view of actually using it in a course. And Anandu, Sharath, Pinku, they are our staff at IIT Palakkad, and they were the people who actually did the first fabrication runs. Abhinav subsequently joined in the fabrication, and now recently Aditya has also joined in. All the kits that you are seeing here are actually fabricated by Aditya. All of these kits are actually fabricated in-house in our lab. Only the PCB is manufactured outside. That means the bare copper PCB, the green thing, comes manufactured outside. All the component assembly is done in-house. Okay, so it's also a learning for us to be able to fabricate something that looks reasonably professionally done. Okay, so we'd like some feedback on the design as well. So that's what we have here, and maybe we can, as I narrate, let Abhinav just show you the components, and you can also see them on the screen. So we have already discussed a lot of it. I showed you what the small board is for. It gives you 0, +5, also 2.5 volts and 3.3 volts. The choice for single supply operation was twofold. One is the fact that we want to keep the cost low. The other is also the fact that if you take any modern electronic system, you really don't have the negative supply with you. All your phone, laptop, everything is working only on single supply. The days of having negative supply to work with have actually gone. So though for teaching, it is convenient to take an op amp and say +15, -15 and then work. In practice, you really have op amps which are called as rail to rail op amps, which means that the saturation voltage on the plus side goes all the way till the upper supply, and the saturation voltage for the lower goes all the way till the lower supply, and they are single supply. So single supply rail to rail op amps are available. Those are the ones we are using, and those are the ones we also use when we use this kit to teach. Okay, but we have got feedback that having a negative supply is useful, so we will incorporate that in some form in the next version. And then you have the main board. Maybe you can just show, as I'm you can use a screwdriver and just show. So you could see the, yeah, so that's the main board, and this board is actually sitting as a hat on top of a regular Arduino. We'll tell you why we chose it that way. Okay, fine. And you can see that we have some stickers which tell you the scope output and the signal generator, sorry, scope input and signal generator output. Okay, so just see that. You should be able to see. So that tells you the signal generator. Signal generator gives you square, sine, triangle. That should be enough for you. And it's a 2-channel scope. Okay, fine. One of the connections that you need to do when you're using this, convenient, not necessary, but convenient to do, is the following: that our oscilloscope, our signal generator, the signal comes 0 to 5 volts. Okay, so if it's a sine wave, it gives you a constant amplitude 0 to 5 volts sine wave. You can change the frequency using the app which is there on the laptop. So, but for your applications, you may want to reduce the amplitude. Second is, you still want to use op amps in many of your analog experiments. So nominally, you have to shift what you would think in a textbook being at 0 voltage, you would have to shift it to VCC by 2. That is 2.5. So you have to do the shift of 0 to 2.5. So what we have done, that power supply board which is there actually helps you to do that. So when you take the signal from the signal out, from the SIGGEN out, that will be 0 to 5 volts. You give that to, on the power board, you will see that there is an in. Can you see that? On the power board, there is an in. You can, if you read on the board, it's easier for you to see. On the power board, there is an in on the left side. You give that on the in, and then you take it from the out. Has everyone seen that? You see the in and the out. And there's a small potentiometer there, and all of you have a screwdriver. So when you do this, essentially what it does is it takes this voltage, which is 0 to 5 volts, a sine wave, and then when you change the when you use the pot, it will change the amplitude, but it will still ride on 2.5. So for all your practical purposes, 2.5 is like your 0. So if I have a textbook op amp circuit, anything that is at 0 will go to the 2.5 line. Anything at minus 15 will go to the ground line, and anything at plus 15 will go to the 5-volt line. That's essentially what you have to do. Okay. So as long as you use a rail-to-rail op-amp, you can do all the circuits that you normally learn using this. If you use a standard op-amp, the only challenge would be that in a standard op-amp, the output voltage does not go all the way till plus and minus. I think you have not yet done your analog course. When you do that, you will appreciate it better. If I take a standard 741, which is a commercially available, which is a most commonly used op-amp, the output goes, even though when you run plus minus 15, output will go to maybe 12 volts on the plus side and maybe minus 12 volts on the minus side. There is a headroom of 2-3 volts on the top and at the bottom. That's not there in what's called as a rail-to-rail op-amp. That's all. Okay. So you've got the idea. We want you to wire up, some of you to wire up an analog circuit, some of you to wire up a digital circuit. Okay, just to see. So we'll give you the circuit to wire up. Yeah, this is our evaluation. So as I told you, so we have a 2-channel oscilloscope. The oscilloscope itself can show you up to plus minus 15 volts. Okay. There is what we call as a DDS signal generator. DDS talks about the algorithm that actually implements the synthesis of the signal, and that's called direct digital synthesis. We'll talk to you about that. Okay, so it gives you square, sine, triangle up to about 25 kilohertz, works well. We have a Bode analyzer, which means you want to find the frequency response of a circuit, you can actually use this. An FFT based spectrum analysis tool. So you have a square wave, I can find out the components. And then 2.5 volts, 3.3 volts, 5 volt DC are available. Okay, so that's essentially what we have. Let's proceed. Okay, so if I look now at the GUI, you will see that there are a few things that may be of interest to you. Okay, so let me use this here. So on the GUI, you will see that this is the main scope and signal generator console. You will see your signals here. When you press connect, it should connect to your hardware. Okay, and then various channels here. Something regarding trigger, because this is like a regular oscilloscope. I'm not sure how many of you have experience using a regular standard oscilloscope. So not all of you have actually used the. That's interesting. Okay. Okay. So we'll tell you a little bit about what how we mimic the functionality of a regular oscilloscope here. Okay. That's to do with what's known as the trigger, and then how you can capture. So this is a 2 megasample per second maximum sampling rate scope, and it's a 2-channel scope. But we have some clever ways by which you can see, for example, the output of a counter which has even 8 bits. Okay, so there's a clever way in which we set it up so you can actually see 8 bits or even 16 bits if you so choose. Okay, so that's something that we can see. Then the sampling rate here, the channel 1, channel 2 gain. We'll walk you through all of this. You may not be able to see because the screen is quite small. Offsets, I'll tell you what those offsets are. Trigger, okay, and the signal generator comes here. So what I'll do now is to just quickly give you a demo so that you see what's there. Okay, so let me see. I've connected. Just press connect. I connect. So I have now set the frequency at 1 kilohertz. Let it run, and I'm just running the oscilloscope also. Okay, so just show them the sign from the signal generator on the scope, and then as you adjust the pot, how things change. So what we're doing, so those of you who have the hardware with you and have got the software also, right now you can use 2 USB ports from your laptop itself to power. Nothing will happen. Okay, we are confident the fuse blows. In fact, the fuse blows sometimes. It's a fuse which is we have optimized to be on the lower side. So sometimes, even when you're doing something useful, sometimes you might blow the fuse, which is better than having to blow the fuse or not having to blow the fuse when something dangerous happens, right? Okay. So we had something else wired, so he's just checking that. So you'll see the different trigger mode. Just press run again. Okay. So you'll see that the sine wave is running around, and as you change the pot, you will see that the sine amplitude changes. Can you change the pot? So let's go through this and then we'll come back. So that's where we started, and then that was the first demo piece. This was what we shipped during COVID. You'll see that slowly the form factor is improving. These are the first 6 we sent to IIT Madras. And then this is the one that we then IIT Madras used. Those are the students who took those kits home. Okay. So what I've done now is to take the GUI and then basically annotate and tell you what the important system aspects that this kind of electronic system needs. You have not yet got the software. So looking at, just look at what I've annotated. Okay. So we have, so on the top, I've said that there is a USB interface. So you're connecting this system to your laptop. So you need to have a USB interface. So based on the GUI, I'm trying to identify what are the hardware components that your system should support. Then let's look at the left bottom. So I say timer and a digital to analog. So essentially you are trying to make a signal generator. So for a signal generator, I need to have some way to set the time base. So there should be a timer. I should be able to generate signals. So I need to have a D2A converter. Okay. So that's there. Then let's go on the right hand side. So above we have, I've said that there is an A to D converter. So for the oscilloscope, it's obvious that you will know that we need to have the A to D converter. But just having the A to D converter would not suffice, because one of the things in an oscilloscope is that when you typically use an oscilloscope to see periodic signals, right? So one of the things in an oscilloscope is that you should be able to see a periodic signal appear stationary, right? And that's achieved using your trigger control. How many of you understand what trigger is? Okay, so for the others, we'll walk you through. I have a slide. So essentially, you have a signal that's just running around. It's a periodic signal, but you are trying to take a snapshot of that periodic signal, and you take repeated snapshots. But you want to take the snapshot in such a way that every snapshot overlays over the older snapshot, so that your waveform appears to be stationary within the frame of your screen. If you don't trigger the signal properly, the waveform will dance around. Okay, it will dance around. So it's not sufficient merely that you have an A to D converter. You have to tell the A to D converter when it needs to start doing the A to D conversion. Okay, so that is achieved using a trigger command, and that's why I have drawn the I've written it as pulse width modulator, because that's the way we are actually implementing the trigger control. I'll come and talk to you about that. But please just note here that the A to D converter has to be taken along with the pulse width modulator. How many of you know what pulse width modulation is? Okay, so for the others, we'll show you. Okay. Apart from that, there's a gain block. So you have signals. There'll be some signals which are very high. There'll be some signals which are very weak, and so you need to have the capability to set the gain for the various signals so that you can see them on the scope. Okay, so there is the gain block as well, and so the gain block is achieved through your GUI. So that means you have a gain is achieved using an amplifier. That gain is programmable, so you can set it through your GUI. Okay, then I've already spoken to you about the trigger part. So for the trigger, okay, actually I can't read from here. That's why I mentioned something slightly incorrect. For the trigger, we use an internal comparator. So I'll come to that and tell you what the comparator is. And then you also have the pulse width modulator to do offsets. That is, you can move your waveforms up and down. So that's for the offset. Okay. So basically, if you look, so you have any electronic system, you're trying to do something. So what would you first do? You would first make the specs, and after the specs, you will have some kind of a rough design that gives you what the functionality or a mock-up is. So many of you are familiar making apps, right? What would you first design the app? Design the app means you're just putting the buttons there. You're not, the button is dead. You click the button, nothing happens. But your first thing is, okay, let me take a piece of paper or something on the computer. Let me at least put down all the blocks that I want. So when I'm trying to make an oscilloscope and signal generator, these are the blocks that I need, right? And those blocks will then, because this is a hardware system, those blocks will then correspond to some things in hardware that we will also need. So we have to make that connection, right? Now comes where your experience plays a role. These are the things that you need. These are the hardware blocks that you need. But what is the hardware component that you're going to choose? Component or components that you're going to choose that will give you this functionality. You might, you can buy a dedicated USB interface chip, or like you people work, it's like something like like an interface board that you can then stick somewhere else. Okay, that's one option. Then for your ADC, you might have just an A to D converter chip that you then have to interface with some microcontroller. Or you would try and choose a microcontroller which is a system on chip. You will try and choose a system on chip which gives you all of this functionality within the same chip. If you do that, your component count comes down, and it's also likely that your cost comes down. So when you look then at the family of microcontrollers that exist, everyone has their favorite, right? Some work with the PIC microcontroller series, some prefer the Atmel series, some prefer the TI series, some the ESP series, some the STM series. So there's a whole zoo of these things. And each of these families, when you go in, you will find that there's one list of 320A, 320A1, A2, they're huge numbers. And each of those, when you look into the data sheet, will tell you actually as to, okay, this one has this, it has 4 counters, this has 2 counters, that has 2 ADC. It's a mess. Actually, if there is a, if somebody is interested, some kind of an AI based tool that tells you for this application, this is the best microcontroller to choose would be actually good. The data is there. Is there something already there? What is it? Flex. Okay, so I don't know about that. Okay, good. So once you have written down what are the specs that you need, then and what the functionality you need is, you then choose your hardware. Okay. So we are in the next version that we are right now making, we will remove those potentiometers which need to be operated using the screw. We'll give you a nice knob. That's more robust, right? So it's not too much of a cost increase. We found that the cost increase for that compared to the cost that you need to do, that you have to incur when you have to supply the screwdriver, it's the same. You don't think about it, right? That you think, oh yeah, screwdriver, why to give? Everyone will have a screwdriver. That's okay. If you're working in the lab, everyone has a screwdriver. But the moment I'm sending it as a kit to somebody, right, you need to have the screwdriver as well. You might you have heard about the story when I think the Amazon has this thing, right, which controls, or Google, one of these guys that has uh, the 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 set of things that you can use to control the lights, control everything. What's it called? Those smart things. So I think when they started, there is a story which they were trying to see why is the uptake not good. They found that the final conclusion of that exercise was that they were not shipping the screwdriver. So because to fix that on the wall, you need a screwdriver. Most houses don't have the screwdriver, so that becomes the block. And so they said, okay, we'll just ship the screwdriver as well. They are big guys. Shipping a screwdriver does not make much of a difference. But for us, the screwdriver is 40 rupees, 50 rupees. So yeah, so these are things that we pick up. Okay, so we'll show you the other things. Maybe you can show the. So let's see the trigger first. Okay. So let's go to the repeat board. Okay. So this is what I was indicating to those who did not understand what I meant by trigger. We have not triggered the waveform. You're seeing the waveform, right? But you're seeing the waveform dance around. Why is that? So what is not repetitive? The waveform is repetitive. The waveform is repetitive. There's no problem with the waveform. Why is it moving? It's appearing to move. It's not triggered is the technical thing, right? I've been saying trigger. So you're saying it's not triggered. That's correct. But physically, what do you mean by saying that it's not triggered? You have to continuously read the values. Otherwise, if there's a change in the waveform, you'll not catch it. See, an oscilloscope is supposed to see the waveform live. Your waveform is nominally periodic, but it's not like if I take the first period and the second period to the last decimal place, it's identical. It's not like that, right? It has to be different, right? It is changing, but it's roughly the same. Okay, so one thing that you please note. So how are we actually looking at this data on the display? What happens is that the A to D converter is collecting some number of points. So in our implementation, we collect about 200 points. There is a rule that tells you how many points you need per period to be able to capture a waveform correctly. That's your sampling theorem. Okay, so sampling theorem tells you that for one period, you need at least 2 points. That means your sampling frequency has to be twice of your the bandwidth of the system. That's what Nyquist sampling tells you. But you will see practically, if you do that, it's very difficult to reconstruct the waveform. To reconstruct that waveform, you need a very good interpolating engine. That we are not. We are just doing linear interpolation. So to be able to use linear interpolation to show you this, you actually need about 10 samples per period. Okay, so that's why you will see on the right hand side, there is something called select sampling rate. So now I'll read it out, you can't see it. So he is changing the sampling rate. So let's go down to, so this is 1 kilohertz, right? This sample, the signal. So let's change it to, let's sample at say 1 kilohertz itself. Let's see what happens. Okay. Oh, you put that as 2. Okay. So you see that, have you got the waveform correctly? What is appearing to be the period? Look at the horizontal axis. What is the time? 0 to 200 milliseconds. So it's like 0.2 seconds. That's nowhere close to the period of your actual 1 kilohertz waveform. Why? Because you're not sampling it correctly. Now you change it to say 2 kilosamples per second. So technically you should catch it with this, but in practice it never works. Okay, so you need 10. So let's go to 10 kilosamples per second. Okay, you got your waveform correctly. You don't need 10. Maybe you can go to more. More is always no problem. Okay, so this is at how many? This is 100 kilosamples per second. Okay, so we are choosing 200 samples at 100 kilosamples per second. Means what is your sampling time? 200 samples, 100 kilosamples per second. Take pen and paper. Otherwise, you'll put me on a spot. If you ask me to calculate with my half attention on that screen, half attention on the fact that the demo should work and catching the mic, I'll make blunder in calculation. So you calculate. So 200 points. Okay, 100 kilosamples per second. I want to know what is the sampling time. That means for 1 point, what is the time? 100 kilosamples per second. Okay, and I am taking 200 such samples. Okay, so the total time for this would be 2 milliseconds. That you are correct. The 2 milliseconds is the time corresponding to 200 points when the points are being generated at 100 kilosamples per second. Fine. So your total horizontal is 2 milliseconds. That sounds reasonable. You're going from 0 to 2000 microsecond, which is 2 milliseconds. Fine. Okay. My question now is, what is the time for one sample? So it is 2 millisecond divided by 200. 10 microseconds. Okay. So you're sampling at 10 microseconds. It's a 1 kilohertz waveform, which means your period is 1 millisecond. You're sampling at 10 microseconds. Fine. That means you per period, you will get 100 samples. That's why it's looking clean. Okay. So you have to choose. So in a modern oscilloscope, right, you don't need to worry about this. You go press the auto button. Right? You press the auto button. In fact, in our lab, we tell students that in your exam, you are not allowed to press auto to trigger. You trigger manually and show us. You press the auto button, it does its algo and gives you the nice waveform. No, it will automatically give you. Right? So one of the projects I have 3 very smart undergraduate students who took my course just last semester and now working on this kit. So the challenge to them is to implement the auto functionality on this. Okay, it's a good challenge. Implementing the auto is challenging, but then using the auto is, it reduces you have to develop intuition, right? So when somebody said nanosecond, I could immediately say it is not nanosecond. I am not doing any pen and paper calculation here, but I know it is not nanosecond. Right? So if somebody asks you what is the thickness of your hair, my core area of work is semiconductor technology. So every time I go back to that. So what is the thickness of your hair? Millimeters. हाँ अरे भाई इतना मोटा क्या होगा? ना, it cannot be millimeters, no. So as engineers, one of the things is you have to estimate. Okay, what is the size of this room? So we used to have a Professor Kalyana Krishnan in computer science. He used to run this course, and he was a terror. He was a very smart person, but he was very tough. So you would ask these kind of first semester course, like you're sitting in this hall, estimate what is the size of this without using no scale, nothing, just by looking around and looking at what you know. For example, you can see that there's a tile A tile roughly you know is 60 centimeter cross 60 centimeter. Okay, like that. Looking at your environment, can you estimate sizes? So like that, what's the size of your hair? This is an aside, but it's okay. I think we have time. We may not have time. Okay, the human hair is about maybe 10 to 100 microns. Just to put in context, how small are your transistors? Modern transistors are getting fabricated at 2-3 nanometer is all marketing humbug. Maybe 10 nanometers is what is actually getting done. They are saying 1.5, 2 nanometer and all of that. Okay, you take even 10 nanometer and you think that your hair is really thin, maybe 10 micron. That means your semiconductor, the transistor is 1,000th the size of the hair. And you have a billion of those on your chip and most of them work. It's amazing what we're able to do. Really amazing what we're able to do. Putting context again, what is the lattice constant of silicon? You must have studied this in school in chemistry. No, that is the lattice structure. I'm asking what is the lattice constant? The lattice constant of in silicon is half a nanometer. Okay, so that's why I say you cannot have a transistor at 1.5 nanometers. It won't work. Transistor is at least 10 nanometers. A few lattice constants at least. Okay. Let's. So going back to trigger. All right. So the reason why it's dancing is because you are taking snapshots of this waveform at starting from different points. I'll show you a figure to explain that better later. But now we'll at least show you that we can trigger it. So now you will see that there's a red line and there's a green line, right? And then there's a channel 1 offset, channel 2 offset, and then there's a trigger. You can choose the trigger on top by saying trigger mode channel 1, channel 2. So let me say I say trigger mode channel 1. We are on channel 1 or channel 2? Okay, so we have connected to channel 2. So let me say I am on channel 2. You put this as channel 2, so this red is not there. So the next bug which we have to solve actually, is that sometimes when the trigger is not correctly set, the A to D converter gets confused. So it doesn't fail gracefully. So that's what the next bug that we are quashing right now. So it should tell us that, hey, I cannot trigger. So please set the trigger level correctly. Right now what happens is it gets confused. Okay, so these are bugs that we know. Within a week or so we'll have them solved. And you see that green line, right? So what we are implementing is called as level trigger. So you can choose that green line. You can move that green line up and down using the trigger level. Okay, and then what you have to ensure is that that green line is within these extent of your signal, within anywhere within that peak to peak. Okay, and then when you ask it to trigger, what it will do is it finds out where do those things intersect, and it will ensure that that point of intersection is always at the same physical space on your screen. When you do that, it's exactly like you have a fan which is moving, and say you are able to blink at as fast as a rate as the fan. If you are able to blink exactly, then and you synchronize the blinking with the speed of the fan, like your camera, you would have seen in older movies, your wheel going reverse, right? They're all related things. Stroboscopic, you will see the thing not move. Essentially, you're doing something like that. Okay, so why did we go into this? This is a detour, but I'm telling you that this is something that you have to implement. Having just an A to D converter is not enough. A to D converter is there in your Arduino itself, right? But to implement an oscilloscope, you need to implement a robust trigger functionality. The bug that I'm talking to you about is the following: that I'm asking it to trigger, but I have set the level to be out of the range of the signal. It's a very simple bug, right? It's out of range of the signal. So what happens? It's not able to find the intersection. What should it tell me? I am not able to find the intersection, or in better words, just tell me that your trigger level is out of extent. Please reset. That's all. So we have to just implement. Okay, fine. So we decided that we will go with this at X mega series of processor. That's not the one that you're seeing, by the way. There's a story as to why it's not the case. Okay, so the at X mega is one of these very, very capable system on chip based microcontrollers, which has all of those things that we need. Okay, I'm not sure whether you will be able to see, but this is not for you to see. I have highlighted. So it has a high speed USB interface built in. So you don't need any additional USB to serial converter when you're using this. Then for our scope, trigger, and capture, it has the A to D converters, and it also has comparator, 2 analog comparators. So that helps us, because to do this intersection, what I was talking about, you need the comparator. Okay. Then for the offset of the scope, we are going to use this PWM module. I'll show you why. So that's available. Then this is where this particular chip really shines, and this may be little beyond what you people are familiar with, but please note that the oscilloscope and this particular electronic system is concurrently running 2 tasks. The signal generator is one task, the oscilloscope is another task. They both have to happen at the same time. In a more, if you think about this little in more detail, if you have one processor which is having to do both of these things, what would happen? It will either be doing the signal generation task or it will be doing the oscilloscope task. You will not have both of them happening at the same time. Then you have not made, then I've either made a signal generator or I've made an oscilloscope. Okay, but that's not what we wanted to do. I wanted to have a system which gives me both the functionality for a signal generator and the functionality for an oscilloscope, so that I can use this as a replacement for all my tabletop equipment to run a lab. Right? So these two have to run concurrently. How is that achieved? So there is this concept which is known as direct memory access, or DMA. You would not have been introduced to it in your introductory course on digital. Maybe in your embedded systems course you would look at it. This particular processor implements DMA. What DMA means is that different modules, different hardware modules of your system on chip or of your microcontroller can talk to each other without the processor getting involved, in very simple terms. Okay, this particular chip actually enables a DMA operation. So between a D2A converter and a timer. So between the timer and the D2A converter, you can have direct memory access. That means, so DMA means that memory is also involved. So memory, D2A converter, and timer can operate without the processor. The processor, every once in a while, maybe you would have to raise an interrupt to change the frequency. But once you do that, it will run. Okay, so that is critical. And this particular processor allows that. As a result, we could implement in our first prototype, the one that we used during COVID, the functionality of both the oscilloscope and signal generator on a single chip. And that chip cost us at that time, during COVID, all components were exorbitantly priced. At that time, it cost us about 800 rupees. What happened then? We should have bought. We thought 800, so we bought only about 20 and we kept it and we did our work. But about a year after that, when Janakiraman approached us, those chips were out of stock. We just couldn't get those. We tried, we were talking to some Polish vendor here, there. All those guys were just looting us. Obscenely high. They were, instead of 800 rupees, which itself was high, they were charging 5,000, 6,000, and we didn't know whether that chip would actually work or not. You buy 100 of those and they don't work, what would you do? You can't do anything about it. Okay. So that's when we had to actually do a redesign. And what you're seeing is that redesigned system. So in this particular system, what actually happens is that you have two processors. One processor which is on the Arduino. It is doing the functionality of the signal generator. There is then the processor on top, which is a TI processor, which is doing the functionality of the oscilloscope. The TI processor, unfortunately, does not have DMA. So you cannot, that's why you need to have two processors. Additionally, it does not have the gain, the programmable gain amplifier capability inside. So we have to bring that out. So you will see that there are two more ICs for that. Next, it has only one comparator. It does not have two comparators. So if you had two comparators, then it's easy. For each channel, you have the trigger and you have its corresponding comparator. Here you have only one comparator. So we had to do something to use that. Okay. And it does not have the USB interface as well. So if you just look at it, the TI chip even is actually more expensive than the ATX Mega chip, but it does not have some of those functionalities. And then we had to do a very clever use of the hardware which is available on your Arduino and what we have on the TI chip with the PGA, with the programmable gain amplifier to achieve what we wanted. All of this with a cost objective in mind. If there is no cost objective, electronic system design is not that hard, right? I buy the best of each and put it together, it should work, right? So now let's go in and very quickly go through some of the details. I have already given you a feel for these things, but this is to look at the same data but more precisely. So again, from point of view of my specification, I have an input signal that can go plus minus 15 for my oscilloscope. I want to be able to see it. I'm using the inbuilt A to D converter on the microcontroller itself. Most of the A to D converters have some range. I've just taken 3 volts for discussion. I'm not saying that the microcontroller that we are using has 3 volts, but just for discussion, it will be close to 3, maybe 3.3. Sometimes it may be 5, depending on how you configure. Okay. So let's say this. I have an input which is going plus minus 15, which means my total peak to peak spread is 30 volts on the input. But my analog to digital converter has an input range of only 3 volts. So I will not be able to. And another thing is the fact that this analog range is also 0 to 3. It's not by, it does, the A to D converter, most A to D converters don't like negative. They expect you to shift, get it into the range, and then back calculate whatever shift you had given and get the answer, right? Okay. So how do you do this? Again, different people will have different suggestions, but what we did was we did a decimation. We do a divide by 10. Then your plus minus 15 will come within plus minus 1.5. So you come to at least 0, you come to a total range, peak to peak range of 3 volts. After that, you do a 1.5 volt offset. I've just chosen these numbers to indicate to you easily, but this is not exactly what we're doing, but similar to this. So now your signal has gone between 0 to 3. Okay. So this is one offset capability that you need. This is a mandatory offset capability. The second offset, this is like a fixed offset. So if you want to only implement this, it's not that challenging. Now go back to the oscilloscope screen. You will see that you want to actually move the waveforms up and down. There's the offset feature there. So can you just play with it's triggered. So you, little bit of thing, it will work. You can move a little bit. So as you move, the waveform itself moves up and down. As long as you're triggered, it will not give any problem. You move up and down, right? So that's an additional offset that you have to implement. So how do you implement the offset? Now go back. Why would you need this? You have 2 signals, for example, right? You would want to take one signal, keep it up, another signal, keep it down. I'm sure you would have done that with your A to D, with your analog kit also, right? Okay. So just curious, does the A to D, does the oscilloscope on the analog devices thing allow you all this triggering and all of that? It allows you triggering?
Repetitive, there is a functionality of repetitive. If you tick that, it gives the constant as you said. And if you uncheck that, then it actually displays the offset gains.
Offset gains allow. Okay. Maybe different ways of using the same. Maybe the interface is not as standard as we have tried to mimic the interface of a regular standalone. You go to any lab, you will see whether you buy an oscilloscope at 20,000 or at 2 lakhs, these knobs will be same. And we are also trying to get the knob symbol so that we'll get, instead of the slider, we'll get the knob. It should be possible. These are all small things. Now, it's small thing, but it's difficult to do unless you get people who can go in and dig and find it out. And the best, the best resource for that are students. So when you get some enthusiastic students who are willing, and most students have this, we also have this problem, but students have more of this, that they are very averse to touching somebody else's project. If I give you a new project, you will do. So you will go up the sawtooth waveform. Then after 2 months, you will get busy or you will get bored. Then you will say, okay, you'll disappear. That project will still remain. Problem for us is when the next student comes, we have to do a sales pitch saying this is the big picture. These fellows have done up to here. Now please take it forward. If we are bad at the sales pitch, they are not going to take it. They want a new project. Or they will start again from zero saying, no, we don't understand that fellow's code. We will redevelop. They will also go up in 2 months. They will also reach the same place. Okay. So that's a challenge. So finally, I got some students who are smart, who are enthusiastic, and also have taken ownership to look into this code and make the changes. So things are happening. In 2 weeks, we have seen like a lot of changes happening. Okay. Next. So how do you implement the offset? Okay. Remember, there are constraints. If I had a D2A converter, if I had lots of D2A converters, I can use a D2A converter, set the, depending on where I have the slider, I will set a digital value and then use that. I don't have so many D2A converters, but I have these pulse width modulator modules, PWM modules. Basically, what pulse width modulation means is I have a waveform whose duty cycle I can vary. So this is a waveform with 50% duty cycle, which is on for 50% of the time, off for 50% of the time. 0 to some voltage, maybe 5 volts, depending on the microcontroller, maybe 0 to 5, maybe 0 to 3.3, whatever. What if I take the average of this waveform? What will it give me? Half the value. Okay. So I have actually done D2A conversion. If I can change the period of the waveform and do averaging, I've got a analog value corresponding to the period. So that's what the pulse width modulation actually does. Just to check if I've understood. Can you understand the others? So look at the one which gives you V0 by 4. So it's on for 1/4 of the period, off for 3/4. The other one which gives you 3 by 4 V0. It's on for 3/4 of the period, off for 1/4. Fine. Okay, good. So with this, you are actually able to. So what we do is to do this. So I have two. This is not from this kit, but from the other. But the logic is the same. So I basically have two PWM channels here. They're called PWM 0, PWM 1, and then what I'm doing essentially is I shouldn't use the pointer. So what I'm doing then is I have this RC filter. This entire block is just a low pass filter. You will learn in your analog systems class that if you do low pass filtering, you're effectively doing averaging. So that gives me the average value. That's what goes into channel 1 offset and channel 2 offset. So I've generated these entities, channel 1 offset and channel 2 offset. I hope you understand why we need them. Okay, good. Next, let's go to the trigger. Okay, and then we'll see where that offset comes into the actual implementation. Right now, we've just made the offset values. So I have this waveform and I'm going to sample it. So now I've told you already, I've mentioned most of what I've already wanted to mention. I'm just trying to now put them in to re-emphasize with better clarity. So I have say 200 points. So my capital N is 200. Okay. So I am going to have 200 samples I can take with a certain sampling period. Here it is TS. That sampling period is going to be fixed based on the cleverness of the user. If the user chooses a wrong sampling period, he or she will see a wrong waveform. That does not mean the kit is wrong or the oscilloscope is wrong. It means that the user has not chosen the sampling correctly. Okay. Okay. So what's going to happen now? Corresponding to what does sampling essentially mean? You're going to measure the value and of the input analog signal at all those points, convert it into digital. And let me say that the analog values are V1, V0, V1, V2. The A to D converter will convert it and store it as a digital value. Fine. So that is by oscilloscope display. When I do linear interpolation between those values, this is what I'm going to see for the first 200 points. Good. Now, I have come to the 201st point. The question is, where should the 201st point lie? If you don't want the signal to dance around, where should it lie? It should lie on the 0th point. If it lies on the 0th point, you will not see the waveform dance. That's what I'm showing you now. For the next period, again I am sampling such a way that if you see carefully, the last point of this sampling is identical to the first point of the next sampling. And so you see the waveform, I've changed the color and it's not that evident. Just changed from maroon to blue, but they have just overlaid so you don't see it move around. Now you see what happens if you don't trigger properly. So suppose you didn't trigger properly. That means you went to sleep for some time and then started the measurement of the next 200 points. What would happen? Your waveform has got shifted. So every 200 points, if you have this little bit of laziness in starting, your waveform will dance around. Okay. So how do you implement this? You implement it using a comparator. What does the comparator do? It compares two values and gives you a high or a low. Okay. So the at Xbega has the comparator inside. You'll see that there are two comparators. CH1, CH0, somewhere I'm using 1 and 2, somewhere I'm using 0 and 1. Okay, that's that you can understand. So CH0 comparator, CH1 comparator. And you have what does the comparator generate? It generates an interrupt. It generates a signal for an interrupt. That interrupt will ask the ADC to start. How you implement it, that depends on the actual hardware you're working with. But logically, this is what you want. So wherever the comparator goes high, you want the A to D converter to start. Okay, so that's important. The trig 0 and trig 1 are the actual levels that you will generate. How will you generate those trig 0 and trig 1 levels? You can, here what we have done is we use the internal D2A converter itself. Actually, you don't even need to do that because this particular comparator is sitting inside the microcontroller, which means that trig 0 and trig 1 can be specified digitally. The comparator takes a digital input itself. So you don't need to really use any D2A or PWM for that. Okay, now I bring your attention to this first block. In the first block, you will see that there are some resistors, some capacitors. Okay, this is my favorite question in all my exams. And it's a very, very practical, important thing. Again, if you have ever used a real oscilloscope, you will see this problem. And the solution is exactly this. Okay, first you forget about the capacitors. First you forget about the capacitors. Just look at only the resistors. So the resistor values are 100, 800 this side and 100 that side. So what is the division ratio? It's 820, but you take it as 800. 100 divided by 100 plus 900. So it's exactly 1/10. So I told you already about I want to reduce the amplitude by a factor of 10. So that's what that is doing. Forget about the capacitors. Okay. Then if you see there is a CH0 offset and a CH1 offset. Can you see the CH0 offset and CH1 offset? I can't use the laser pointer, that's why. So this is your CH0 offset, this is your CH1 offset. How did those numbers come? They came from the PWM. Okay, what is it doing here? It is basically shifting the signal. So if you work out using your Kirchhoff's voltage law, Kirchhoff's current law, what happens here? If you have that offset, basically you have added this value to your input. So you have shifted the signal into range and you have also reduced the amplitude. So you've done both using few components. Okay, understood? Now question about the capacitor. So what are the capacitors doing? Okay, so this is a very common issue and this is referred to as scope compensation. Your wires usually have some capacitance. Okay, so typically in an oscilloscope, what will happen is if your scope is not properly, the technical word is called compensated. If I give a square wave, you will see one of those three. I'm giving a square wave V in. I will either see V alpha or V beta. V alpha is a low pass version. V beta is a high pass version. Okay. But I don't want to see any of these. I want to see a signal which looks exactly like V in. And the beauty about this network is that one of these capacitors is usually a pot. You can change it. We have not done this here, but you can change, say, C1. When you go to your lab and ask somebody for scope compensation, when you're here, if you have the chance to go to the real lab, at least go and see. Or just look it up on Google. You will be able to see that. So this particular network has one very interesting feature. When R1 C1 is equal to R2 C2, okay, when R1 C1, the product is equal to R2 C2, then V out by V in just becomes R2 divided by R1 plus R2. The capacitances don't come into the picture, which effectively means that a square wave will look like a square wave. Okay, so that's the beauty about this particular network, and that's what that particular combination is achieving. I won't go into that detail too much because you need a little bit of knowledge from analog circuits for that, but we'll not go there. Okay, good. So quickly we'll move on. I have about half an hour more. Let's now go to signal generation. So I wanted to introduce to you this concept of direct digital synthesis first. In the old days, before microcontrollers were very commonly available, most signal generators had some form of an oscillator. You can make a signal generator using your 555, for example. 555 is a very, very common implementation of the older school of analog signal generators. The 555 will give you a square wave. You pass the square wave into an integrator, you will get a sine wave. You take the sine wave, pass it through what's called as a diode shaping network. It will shape that square, that triangle wave into something that looks more sinusoidal, put it through a filter, you'll get a sine wave. Okay, it's a very common way of doing things. But today, most modern signal generators don't do it that way, because you are not very, very precise in terms of what is the actual frequency and amplitude. We are not worrying about the amplitude. That was our design decision. We will not do the amplitude using direct digital synthesis. We will only worry about the frequency. We have a fixed amplitude of 5 volts or 1 volt, depending on which hardware we are using. We will do the amplitude correction using an analog, just using a pot and another amplifier. That's what that daughter board has. Okay. So, look, now I want to generate this triangular waveform. And again, I want to generate it at some number of points. Otherwise, the triangular waveform will not look triangular, or sine will not look sinusoidal. So I have some, it's not called sampling frequency, but it's like a generation rate. I need to generate these samples at some particular rate. How am I going to do this? Suppose I have a waveform which is 1 kilohertz. Okay. That means my period is 1 millisecond. And say I want to have again 100 or 1000 points per sample. That means each time step should be 1 microsecond. No, 1000 means 1 microsecond. That will be good. So every microsecond I have to refresh. I have to get a new value of the amplitude. So what direct digital synthesis actually does is to have a lookup table. But you don't have a lookup table for every frequency. Then there is no end to it. What you have a lookup table, the key which is used for the lookup table is not frequency but phase. Because if you take the product of the frequency, or now here I have taken angular frequency omega, into time, whether I am doing 1 kilohertz or I am doing 10 kilohertz, no problem. Finally, I have to do a phase of 360 degrees in one period, right? Whether I go very fast or I go slow, I'm going to do 360 degrees. It's a periodic signal. I have to do 360 degrees of phase. So phase is a good key for my lookup table. So most of the modern signal generators have this lookup table stored in memory for all of the waveforms you want. Sine, square, triangle, ECG waveform. You will see all those things. You save everything. Then just run through all these points, put it on the D2A converter, you will get your output. The only challenge here is you want to do this concurrently with your oscilloscope, and that you achieve using the DMA. Okay, good. At least overview you've got. Now let's come back to this challenge. So we found then that the this particular chip is not available, and we have to still make this kit. We want something, right? We want a solution. This also, so as we thought about this, we also found that there is an actual use case for this as well. Our final solution is actually a very simple solution. I can use an off-the-shelf Arduino. I'm not doing anything to it. And I'm giving you the code that you need to fuse on the Arduino, that you can fuse. And I'm giving you a daughter board. So I can actually make this daughter board and sell it or distribute it, whatever. If you connect the daughter board onto this, you have yourself an oscilloscope and signal generator. Okay. Well, what were the challenges here? We have to make it. That is always a challenge, but that's also part of the fun. No, if you don't make it, what's the point? Just because you're talking about making, it's something that is very close to our heart, and that's the reason why Abhinav also is a big maker. He makes lots of things. Yesterday he was telling us he was shifting his house. He said a lot of tables have to be shifted. I said, where did you get tables from? He made his own table. So that kind of maker. So he sits in our, like you have the innovation lab. You would have gone to the innovation hub here, right? So similarly, we have a smaller innovation lab. So he sits there, and we use all the machines there to do all of this. So one of the things, talking about making, I see that all of you have used all those small boards which are there. You put them together, maybe on a breadboard or whatever, and you make something. That's one good level. But one thing that I strongly urge that you pick up, you please learn how to make a printed circuit board. Make a PCB. Okay. 3D print a PCB will not work. No. PCBs are made a much more traditional way. If we have time, I'll show you a video. We have net here, right? Through hole surface mount. Today, through holes PCB is no use. You don't get. You very few components you get. Modern components are not made in through hole at all. So you should have the ability to make some of these things, and you can do it at home. Okay, we do it at home. We do it in my home. So if we can do it, and we have given out the procedure to do it, all of you can do it. And we were doing it in our labs using the same procedure until we changed the syllabus. Okay, we'll do the layout in KiCad, and then we print out that pattern onto uh, this glossy paper that you get, the glossy paper that is used for not toner paper, the paper that you use for color printing, photo paper. But use the photo paper on a laser printer and keep the toner on high, so you get the mask made in black. Flip it, put it onto your PCB, and iron it with a regular steam iron. It works. You can do 250 micron, that is quarter tracks with that, no problem. You have to be careful, that's all. Okay, once you've done that, you then have to remove the photo paper and put it into an etchant. Ferric chloride is one etchant, but it's messy. We used hydrochloric acid and HCl. H2O2 and HCl, hydrogen peroxide and HCl. That works better. It's clean. Otherwise, our lab maintenance person will come and shout at us if we pour ferric chloride down the drain. It corrodes. So this is easier for us. And then you have to drill wherever you have the through hole components. The challenge is, how do you do double side? You are doing ironing and all of that. If you do the ironing such that on the top and at the bottom you have an offset, your chips will not work. Okay, so there's a trick, but you can do double side also. You have to be careful. We have one recorded video. I'll share it with you, sir. My dad has made one recorded video of this. It's made with a very old camera, so don't worry about that, but it has the content. Okay, so you can do this. So I know this is what we encourage all our students. If students come to our final product project demonstration with a breadboard, somebody will pull their leg saying, why have you brought it on a breadboard? Why have you not done it on a PCB? What you do on a PCB will last 10 years. What you do on a breadboard will last exactly the time of the lab examination. After that, all the components disappear. Okay, so if you could also use the prototyping board, that's also fine, but that is more work. If once you get the hang of making PCBs, it's very straightforward. Today, you can actually get the PCB made outside also. It's not very expensive. Your JLC PCB is very cheap, but it comes from China, so I don't recommend it. We use a company called Lion Circuits. They are in Bangalore. They're good. We buy everything. We routinely do 4-layer boards in our lab for various things. Okay, so coming back. So we have now this challenge of, I have two processors. One processor to help me to do the signal generator, another processor to help me do the oscilloscope function, right? And I want to keep part count low. So I have not told you which processor is which. Can you tell me which processor is which? One is the Arduino, or the Atmega chip on it, Atmega 328, and the other is the TI. Which is the TI? Which is the Arduino? First one is Arduino. Why do you say that? No, but I have drawn it such that USB to serial is sitting outside, right? You are right. Okay, I just drew it like that. Okay, so the Arduino board, the chip on the Arduino board, the actual microcontroller on the Arduino board does not have a USB interface. No inherent USB interface. The USB capability of your Arduino is achieved using, there is one more chip on that. Okay, and that is a pain actually. We realized that it's really difficult to get this reliable enough to sell in the open market. Open market in the sense that I told you, if you buy the regular Arduino, which has the DIP package, the DIP package, okay, then however I send you my hat, you connect it on any Arduino, it will work. No problem. But those DIP packaged Arduinos are actually expensive. Now they cost almost about 700 rupees. You have Arduinos at 200, 300 also. But you check what is the package on those. It's usually the surface mount IC. And you'll see that the surface mount version of the Arduino uses one Chinese off-the-shelf USB to serial converter. It's called CH340. But in that itself, there are a whole lot of clones to keep the cost low. And those clones are all undocumented. They will work for the Arduino. But the moment we try and do what we are trying, it will not work. Okay, so we had this thing. We bought 200 Arduinos and we found that our previous slot it is working, this slot it is not working. Then we had to spend time to actually debug what was the problem. We went into the Arduino board and changed a few resistors. That's all it needed finally. But debugging that took a time. We had to change a few resistors. Instead of 10K, we made it 100K. It works. But too much effort, right? So anyway, coming back to this. So the USB to serial capability is coming from the Arduino board. My TI chip does not have any USB. So what have we done? So you see the signal path. And this is a non-standard use actually. So what you've done is on the Arduino board, we have inhibited the transmit functionality of the chip. So when I send data, I am sending a serial stream from my GUI to the hardware. That is coming through the Arduino board. Okay. But the data I send is tagged because every serial stream, I can put whatever I want, right? So I say this particular command goes to the Arduino. This particular command is supposed to be for my TI chip. Okay. That way I tag the commands. The commands come to both. Both of them receive. Right? This fellow is receiving. This guy is receiving here. And this guy is also receiving here. Both receive. So depending on what is the tag, the appropriate fellow does the job. The oscilloscope has to send data back. Signal generator does not have to send any data back. So that was the trick that we had to use. So the way we have configured, using just the Arduino board and the TI chip without having any additional USB. They're always trying to keep, if you remove the constraint on part count, a lot of what needs to be done need not be done. Right? But you want to do things elegantly with minimum number of components. Okay. So that was one challenge. The other challenge is, now you will see the other things you will understand, right? I have a programmable gain amplifier. I told you now that the programmable gain amplifier in this TI board is not inside, it is out. And the other challenge is the TI board has only one comparator, not two. Earlier, I had two comparators, it was easy. Now I have one comparator. So what do you do? So it so turned out that the programmable gain amplifier we bought has an SPI interface. There's another serial interface. And you can use that SPI interface to, it's actually each of these programmable gain amplifiers is a 2-channel one. So you see that this PGA has 2 inputs. This PGA has 2 inputs. I've taken channel 1. This is that RC network and the offset. So that you don't worry about. I have taken the channel 1, sent it to both PGA 1 and PGA 2. I've taken channel 2 also and sent it to PGA 1 and PGA 2. And I have this SPI command which is coming from the microcontroller to both the PGAs. So depending on whether you are triggering by channel 1 or channel 2, I choose which routing I want, whether I want this signal to come via this or I want to come via this. So that whichever one needs to be triggered will come on this channel so that it goes into the comparator. Okay, that's the logic. Now, many times you would wonder, right? This is a very practical thing. I also face this problem. Point is, you have chosen the hardware first. Based on something, okay, you look at the data sheet, preliminary, this works, so I've chosen this hardware. Then I start doing my work. Along the way, I find, hey, no, this may not do that. Now you have two options. One is you choose new hardware, or you look and try and figure out how to make it work. This is always there, right? And many times I think the habit is change the hardware. That's the easier thing. Right? Maybe many times little thought into, can I use this hardware? I have chosen the hardware. I might have used some logic to choose that hardware. It is possible that as I am doing the project, that logic has got a little deflated. Right? My knowledge about what I am doing improves as I start, right? So when I start, I have some idea I've chosen. After that, so this is one example where we did not change the hardware. Same hardware, figure out how to make it work. And now it works reliably, no problem. That's the one that you people are using. Okay, so just last bit. So also this Arduino does not have a DAC, does not have a D2A converter. So there is this simple thing called an 8421 DAC. You will read about it later. But essentially, you take an op amp and you have resistors which have a particular ratio, give inputs, it will do the addition and give you an analog signal which is proportional to whatever is the digital word. So that works. Anyway, that we don't need to get into. All right. So this was the story about how we came to this. We'll show you a small video on some of the fabrication aspects. So what I want to indicate to you here is the following, that this process involves a lot of iteration. You design a PCB, we send out the PCB for manufacture, the bare PCB comes. Then we have to do the component assembly. How do you do the component assembly? Some of these chips are really small. You look at the things, right? They are small. In fact, you can do this assembly by hand using a regular soldering iron. If you should develop the skill to do it. You can do it. Okay. In fact, in our skill test for staff, we give this as a test. Can you solder this small? So if you are a technician, you should be able to. If you don't, then you go, please prepare and come. But if you are trying to assemble 100 boards, doing it by hand is really irritating. So we thankfully have in our lab a capability to do SMD assembly. So the process is fairly straightforward. You have what's called as a stencil. You can make the stencil from your PCB manufacturer itself. Stencil basically has holes corresponding to the solder pads. If you don't have access to a stencil, you can also use a laser cutter and make the stencil. That also works. We do it many times. For slightly larger things, it works. Again, we do a cost optimization. If we're doing 100 boards, it makes sense to get the stencil. If we're doing 2 boards, stencil cost is more than the board cost by factor of 10. So it's not worth it. Okay, here we made the stencil. So then there is something called as a stencil printer. Stencil printer essentially allows you to align your PCB along with that stencil. Allows you to do rotation, up, down, left, right alignment. You have something called a solder paste. It's like your soldering material, but it has the consistency of toothpaste. You take that, put it on the stencil. You have a squeegee, which is the same thing was used to mop, right? You rub. What happens is that the solder paste gets transferred onto the pads. Then you take the PCB, which has this solder paste on the pads for component assembly. You can do the component assembly by hand, or you have robotic machines that do that. So we have one robotic machine that does this. But before this, we were doing it by hand. You can do by hand. I'm not saying that this is needed. If you're trying to do 100, 200, you need to do the robotic thing. Otherwise, the fellow who does it by hand is going to kick you, right? And if you have a company and trying to sell it and you start doing it by hand, you will be paying more salary than the money that you're making. Then no point. Once you place the component, you put this board with the solder paste with the component into an oven. It heats the solder and then fixes the component. So this is called reflow soldering, and that's what these boards are assembled with. Okay. So that is the board. Apart from the board, what are the other things you think we need to do here? So we have to cut the acrylic. So right, the acrylic is all laser cut. Then you have to make the mounts and things like that. Final thing is the artwork. That's also critical, right? So you have to get the sticker made, and you have to stick the sticker onto the acrylic without any bubbles. So each of these things, and what I'm trying to convey to you is not that what we have done is very great, but if you try and take anything and take it from the stage of a prototype to a product, you have to try and incorporate some aspects of look and finish into your product. Otherwise, nobody is going to buy it. If I give this to a professional designer, he will point out or she will point out a list of things which we can improve on. But to whatever we can try and what we can understand, we have tried. So you have to stick this sticker without getting air bubbles. So there's a way. You go and ask that fellow, the fellow who sticks these stickers on the window, "Bhaiya, kaise karte ho?" Then he will say, "Why should I tell you?" No, we are not going to go and stick things on the window. This is not, we are not eating your business. This is what we want to do. Once you show them that this is what you want to do, they themselves will tell you what to do. And if they didn't tell you, it's not easy to do it, right? The trick is to put soap water and then stick this on that when it is wet. That is the non-intuitive part. You have to stick it when there is water on it. And then you use a squeegee to remove the water. That's how you don't get the bubbles. Okay. Non-intuitive. But that's the trick of the trade. So the fellow who does it on the window doesn't want to tell you because that is his business. right? You go and start sticking on windows in your office or in your house, then he's going to lose his business. So he won't tell you fully. So you try and figure out these things, right? So that's that. So we have one making video, and then we'll quickly show you some experiments. This is the famous water. This was one of the older versions that were made. Okay, good. So the nice thing is, first time you do it takes a lot of time. The second time, sticking, all that went very fast. So you figured out. Now we know how to do it. Okay, so we'll do the second part of what we wanted to do. We thought that you people will wire up, but maybe that's a little difficult. Those who have something, you can look and see if you can see signals. Yeah. 5 hertz. 5 hertz. 50 hertz you should be able to see. 1 hertz will be difficult. Because for 1 hertz, you can do it. I think we have tried 1 hertz. It will work. It will work. You can take 1 hertz. Yeah. So see this the signal generator that we have on this version, it's effectively only one channel, in the sense that you can set the square wave will have the same frequency as your sine wave. Okay. Because of the challenge of this, the ATX Mega version had 2 independent channels. We could not get that to work on this because of the hardware. So when you, just to tell you, so if you want a 5 hertz square wave and a 5 hertz sine wave, it will work. But 1 hertz square wave and 5 hertz sine wave, you won't get.
No, both the square waves, because we are using the square waves as
understand. So this is a single channel signal generator in that sense. You cannot change 2 frequencies.
So using the one channel as a clock generation and the other square wave things.
Both will have the same frequency. You look at the GUI, you will understand. You have only one frequency setting. Right? Oscilloscope is 2 channel, but signal generator is 1 channel. Effectively 1 channel. The square comes free of cost. Okay. But the other version had that. Okay. Okay. So quickly, some of the kind of experiments that we do. So this was one of the experiments that we recently ran in our lab. You will do something similar in your analog circuits lab. So this is an inverter. Okay. It's a CMOS inverter. Many of you would have looked at it. Some might not have, but that's okay. Okay. And inverter has this kind of characteristic, right? When the input is low, output is high. When the input is high, output is low. That's where you use it when you're trying to use it as a digital circuit. But interestingly, you can use this as an analog circuit as well. Analog circuit means as an analog amplifier. Amplifier means you want to have gain. That means D derivative of the output with respect to the input should be very high. If you look at this curve, which region do you think has the highest derivative of dV out by dV in? That vertical steep edge. Okay, so if you can bias your amplifier there, you will see that the gain is the highest. Okay, so that's what we do. You will learn later that if you just put one resistor between the input and the output, you can actually bias the amplifier exactly at this point. Okay, so once you have biased the amplifier like that, I can actually make an amplifier using the inverter. Okay, so to do that, so this is one of the experiments that we ran recently based on Nagendra's and Shanti Pawan's assignment book, but some modifications. So in inverter, I want to use this inverter as an amplifier. So I have to bias it at the transition region. So this is just spice simulation. I have some parameters. And so if you bias it as an amplifier, you see that you have decent gain, right? My input is quite small, output is quite large. You get a gain of about 50 using this. Not problem. Inverting gain of about minus 50 using this. Okay. So this is the first thing. So we will show you all of these as we have wired up on the board, right? Then one challenge in any such amplifier is the following. If I take out this particular IC and stick a different IC, same number, but a different IC, the gain will change. Because the gain in this depends on what's called as the transconductance, GM, of the specific transistors inside. And if I take like, all resistors of 10K, if I measure, one of them will be 9.9, another will be 10.2. So depending on that variation, my gain also will change. So the way you avoid this is to actually make a feedback amplifier. Like you make an inverting amplifier, a non-inverting amplifier using an op-amp. There you don't care about the characteristics of the op-amp. You always get the gain given by minus R2 by R1 or 1 plus R2 by R1, depending only on the component values, right? So similarly here, it's small, but you can see this R2 and R3, we have chosen 20K and 10K. This is an inverting configuration. It should give us a gain of 2, minus 2. But you will see that the gain is actually not minus 2. It's very, very low. The input is going up to 15 and the output is going to 10. Or sorry, input is going to 10, output is going to 15. Okay, the axis is, but no gain. Why is that? That's because actually, when you have an op-amp, the gain of the op-amp is very high. It's 10 power 4 or 10 power 5. The open loop gain of an op-amp is very high. You will learn these things in the next class. I'm not expecting that you will all pick up what I'm saying right now. This is just to give a feel of what kind of experiments we can do. The gain of this amplifier is only 50 nominally. So that's not good enough. So what you do is you cascade 3 of them. So 50 into 50 into 50. How much is that? 50 into 50 is 2500. Into another 50 is 62500. So you got a gain of more than 10 power 4. Okay. And then you do this R2 by R1. Or in this case, we have called it R2 and R3, 20K, 10K. But there's something interesting that happens. And that's actually the heart of what you will pick up when you do your analog circuits class. When you do the simulation, and we'll show you in hardware also, the guy does not actually work as an amplifier, it oscillates. Why? So you possibly don't have the background to do this. But long story short, no, it's not because of that. It appears like that, but it's not. That's not the reason for the oscillation. The reason for the oscillation is each of these amplifiers, I am telling you, has a gain of 50, but that is the DC gain. They also have a frequency response. So when you take 3 such, and the frequency response is roughly a first order system in this particular case. I take 3 of these first order systems, put them in cascade, you get a third order system. You might have learned somewhere, or you will learn later, that when you have systems in feedback, you need to ensure that the poles of the closed loop system are on your left half plane. If the poles go on the right half plane, the system will start to oscillate. If this does not make sense to you, forget about it. Okay. But basically, it has something to do with the frequency response of each of these guys. Okay. So when you have this kind of naive connection, it so happens that the poles of this closed loop amplifier are actually sitting on the right half plane. So this guy actually works as an oscillator and not an amplifier. So the solution to this is to do something called as compensation. And the compensation technique here, the easiest compensation is just to go and stick one big capacitor here. Why, you will learn later. Okay. This is called dominant pole compensation. And once we do that dominant pole compensation, you see the output. Okay. This is LT Spice simulation. We'll show you on hardware also. Input is 0.02, that's 20 millivolts. And output is 40 millivolts. Okay. So the logic works that the intuition as to why the single stage amplifier put in feedback does not give you the gain as expected is because of the finite gain of that amplifier. It's only gain of 50. You put 3 amplifiers, you have the problem of the frequency response and the system becoming unstable, oscillates. You put this capacitor, stabilizes it, and you will see the gain of -2. Okay. I went through this in exactly 3 minutes. When we ran this as an experiment in the analog circuits lab, it took the students 4 afternoons to work out. Okay. So I don't expect you to pick it up that quickly, but we just giving you a context for this so that if the demo is working, we can show it to you there. Okay. So we'll first show you the single stage amplifier, which gives you some gain. So in our new design, we are going to do away with the separate daughter board. So now for the Tata project, because they need 250 or some crazy number for donation. So what we're trying to do now is we'll go back to the ATX Mega design and we'll incorporate plus minus supply, and we will eliminate the requirement for a separate daughter board. The same PCB, the problem when you have 2 PCBs is it doubles our making time. For the robotic pick and place, having to assemble another few centimeters squared is easy. But if we have to assemble it separately, you have to reset all the alignment, components, mask, everything. So that hopefully next 2 months we should have that. So the other example is possibly something that you will be familiar with, is a simple counter made with flip-flops. Are you all familiar with flip-flops? Okay. So I've not given the output. So you tell me the output. I have forgotten my digital. So what flip-flops are these? They're D flip-flops. Okay. So they're D flip-flops and a very simple ripple counter only. Okay. So I've told you the answer. So it's basically a counter. Okay. So the reason we did this is we want to show you 4 outputs, even though we have a 2-channel scope. Okay. So that's what we want to show you here. Okay. What is the point in using hardware? So where would you do it then? In the graph. See, what will happen is that finally your A to D converter, the quality of your A to D conversion depends on what is the magnitude of the input that you're giving. If I have a very, very weak signal at the input, my A to D is going to be poor. To that poor A to D, if I do digital gain multiplication, I'm still going to get all the artifacts of the poor A to D in my result. So you would want to actually improve the input stage gain first, then take it through. Remember that the way we have set up has a mandatory reduction by factor of 10. We're doing that only then we're doing A to D. So already we are struggling. We are doing in a reduction of 1 by 10. Over and above that, you have a weak signal, right? The original plan was to show you the initial signals and all of that, not on the board that we had wired. So use a different board. So when I asked him to show that, he had to remove those connections. As a result, we have to redo those connections. It may or may not work. Correct. No. Exactly. You have only one signal generator. You have. Okay. That they have configured like that, but the solution for you is just to have a 2-channel signal generator, right? Yeah. So that in our new version that will be there. It will have 2 channels. Actually, our old version already had 2 channels. We removed 1 channel in this process of having to figure out a replacement due to the part shortage. We also had digital IOs. So you could do 8-bit digital IO directly through the GUI with the ATX Mega. The ATX Mega gives you a lot more functionality. In fact, if there is one chip that you want to really learn, now it's back in stock and it's now cheap also. 350 rupees is what you are getting it at. on Mouser. So it's a good chip to learn, but it will be involved in the sense that it is all programmed in C. So it's not as straightforward as using your Arduino to program. So if you're comfortable programming in C, which is something which you should pick up, that's where the jobs are. So the way we're going to do this is the following: that so we're going to very cleverly use what we know about triggering. Okay. So, and the fact that we know a little bit about the circuit. We know this is a counter. What do we expect on the output? It's a 4-bit counter. So you will have 4 bits of a count. You have the least significant bit, which will run the fastest. You will have the most significant bit, which will toggle the slowest. You know this already. Okay. So, and you also know that everything is going to be driven by the count. Any transition is going to happen only when the count is there, or where the clock is there, right? Or the input is there. So you can use this to your advantage. The way is, so if you look on top, we have 3 modes for capture. One is called single, repeat, and there's a store mode. The repeat mode is what you have seen today. We can move the trigger level and it captures a waveform which is changing with time continuously, but it captures it in such a way that you are getting a stationary view of it. The single mode doesn't worry about triggering. You press single, at that point in time, whatever is the data on the input of the ADC, it will capture and it will throw to you. That is the single mode. Okay. Single mode is useful sometimes, but I don't like the single mode. As a user, I prefer to use, even when I check what the students are doing, I prefer that they show it on the, even the modern oscilloscopes have a stop or a mode. You press that stop button, it will just capture without the triggering, it will show you. So sometimes, by fluke, some result has come, they will press that button and say, sir, the result has come. So you remove that, result has come. Okay. And what the store mode does is that it allows you to capture one set of data using the single mode. It does not clear the canvas. It then puts one more trace using another single mode and another single mode. So given the fact that your input actually can very nicely be triggered using the clock, you can actually build up your entire counter data of 4 bits or 5 bits or 16 bits just by using the store mode. And that's what he will show you. If the live demo doesn't work, then we'll show you the stored data. Okay. I think then our live demo, yeah. So what he's effectively doing is just moving the signals up and down. Okay. And then you press store. Then you get another fellow. You move it, press store, move it, press store. You will get your 4 bits, even though you have only a 2-channel oscilloscope. Okay. So that's useful. So it's a slightly non-standard thing, but useful. Okay. So I think we'll begin to wind up. The other oscillator also works well, but given the fact that live demos have their own challenges, it's nice that we had a fairly large and very enthusiastic audience, and I hope that you people will carry forward all your enthusiasm into this very, very innovative and very different kind of program. I was quite surprised to hear that pleasantly surprised to hear that there are many of you who are doing this full time. So it's possibly not what was envisaged would be expected right at the beginning of a program like this. So that's a lot of confidence that you have put on them, and I'm sure that people like Janki Raman really do a fantastic job of shepherding you through this journey. So good. At some point in time, we will ship a few of these kits to a few of you. We would like your feedback. These things cannot be done like this in a hurry. It has to be done patiently, especially those who have worked with the other kit. We'll ask you, and then we'll get your feedback. And maybe sometime in the future, we might be able to actually supply these things to a larger audience, right? So good. We have a company, it's called Bumblebee Instruments. Our main goal is actually not, this is one of the products we do. We are basically in the business of scientific instruments. So equipment in the electronics and mechanical space for research and R&D. But this is one of our side projects which we think will help. There are a lot of colleges you would not sitting in an IIT. We find it very difficult to believe, but there are lots of colleges, good colleges, where we get a lot of our students from for masters and PhD, where in an entire department they have 5 oscilloscopes. That's what is available. That is the way it is. Nothing. I'm not no fault of theirs. That is the funding situation. They're very dedicated teachers. They teach fantastically. The students who come do fantastic PhD with us. So the students are good. The teachers are good. But that's all is possible in that environment. We hope that something like this, once we've got through all the initial issues, will help people get a feel for actual hands-on work, and help the learning process along the way. So thank you.